Good afternoon, everyone, and welcome to today's webinar on simplifying large channel count DAQ systems, workflows that make setup more efficient. Your microphone will stay muted throughout the presentation in order to avoid feedback. If you have questions, we will address them at the end of the presentation using the Q&A feature of WebEx. However, you are welcome to type in the questions at any time. Our presenter today is Johannes Matos. Johannes has been with HBM since the year 2000. He started in research and development, working on data acquisition software development, and then moved on to doing project and key account management for large channel count applications. He is now the head of the Key Applications Group based in our Darmstadt, Germany factory. Johannes, it's all yours.
Thank you, Krista. And good afternoon, ladies and gentlemen. I'm pleased that you have logged on to today's webinar, Workflows for Configuration of Large Channel Count DAQ Systems. The motivation for this webinar is to discuss the configuration for large channel count DAQ systems as they can occur, especially in applications like structural testing. Let's have a quick overview of the agenda and the topics of today's webinar. In the first item, I would like to look at the configuration process for structural tests with large channel numbers. The next item would be to look at the data sources for the configuration data as they usually occur in these applications. Then having a look at building blocks and workflow options for the configurations. This will include TEDS configuration for transducers, manual input of configuration data, test point plans and merge procedure, import of configuration data from database or Excel sources. Then I would have a look at a few configuration examples for the different workflows, and the last item would be to look at verification of the configuration, and we will deal with the points of minimizing human error and features supporting automated check procedures. The configuration process for structural tests is usually or includes usually different tasks, starting from the planning and design of the test, static, durability or component testing, definition of load spectrum, calculation of expected parameters like strain. Then there is a definition of the test component, the sensors, for example, strain, displacement, load, temperature, the location of the sensors, the sensor wiring, network, power infrastructure, and so on. There is also the definition of configuration parameters, expected values of parameters during the test, calibration data for transducers, parameter data from the test department like gauge factor, location, excitation, voltage, filter settings, and so on. Also, there is the task of the configuration of the test, which is a major task for large channel systems, and of course the verification of the test. Data sources for configuration data are, first of all, the design department. They will design the identification of the sensors, where to place the sensors, expected values of sensors during the test operation, for example, strain at 100% load, required calculated values as ROSET calculations. Secondly, there is usually a calibration department involved or data from a vendor that supplies transducers or sensors. They will usually provide calibration data for the transducer, serial numbers, scaling, and so on. And there's data coming from the test department, including the names, the IDs of sensors, sensor data, gauge factors, scaling information, filters, pictures, comments, etc. All these different configuration data coming from the different departments, from the design department, from the calibration department, from the structural testing, have to be included in the data acquisition test database. This includes sensor information, transducer information, channel configuration, parameters for the data acquisition, predictions, test settings, project settings, and of course also the definition of the graphical user interface. Now, I would now like to introduce the main workflow options that are usually used for large channel setups. That includes the manual input of configuration data. Second option would be to create test point plans and later merge with hardware databases. Third option that is usually used is import of configuration data from databases or Excel sources, for example using TID. And there's also the option of TEDS configuration for transducers. I've now brought up the two acronyms TEDS and TID. In the next two slides, I will explain the meaning of those. TID is an acronym for an identification module that allows you to include an unique, worldwide unique identification number into your measurement chain, and that later on allows you to definitely identify each sensor very easily. Assuming you have hundreds or thousands of channels, it might be quite difficult to connect the right sensor to the right amplifier and not make a mistake by mixing up channels. And that can be avoided by using this TID board. It is, as explained already, in the measurement, included in the measurement chain. It's a unique 8-byte number that is stored in a chip, in a ROM, and can be read out by a USB dongle and also by the data acquisition system. The term TEDS, Transducer Electronic Data Sheet, means this is an IEEE standard to make sensors smarter. Self-described sensor data sheet stored on an EEPROM chip, and it can be used in a one-wire protocol to communicate between the data acquisition and the TEDS chip. The TEDS chip can be included into the transducer or, as displayed here, into a connector. And it is a standard that allows different templates and a language to describe this information. In the table you can see an example of information that can be stored in a TEDS chip. Now let's have a look again at the building blocks and the workflow options for the configuration, and a more detailed look into the different workflow options. For the configuration of large channel count systems and the mapping options for channel-based information, usually one of the below options is chosen, either the manual mapping, a wiring-based mapping, an identification-based mapping, and usually, in addition to that, optional, the TEDS-based setup for transducers. The first is the most simple workflow that you can use. It is the manual mapping, where you would create a hardware scan of your data acquisition amplifier, then put in manually all the information that is needed for your sensors. In this case, there is a small example, the sensor name, for example, the sensor type, excitation voltage, filter, gauge factor. There could be many other parameters that have to be input. Then, once you have done all this manual work, you can then initialize your system and run your measurement. The next option would be to use a test point plan and later merge your test point plan together with your hardware setup. That is an option that makes you independent of your hardware, which means you can create your test point plan before you know exactly the configuration of your data acquisition hardware. Once you have your data acquisition hardware set up at your test article, you can create a setup database and then merge with the test point plan. The result of this merge procedure will be a wiring diagram, and that will allow you to connect your channels according to that wiring diagram, and you don't have to manually input the data that you've already provided in the test point plan. The result is shown in that table, where you can see that you have the wiring diagram that shows you where you have to connect which sensor. So for example, strain sensor 00001 has to be connected to device number 1, slot number 9, channel number 1 in this case. Another workflow, another option is to use the TID, the transducer identification, and import the data according to the transducer identification into your database. That means while setting up your sensors on your test article, you already create a test point plan with the ident information that can be read out by a USB dongle directly, for example, to an Excel sheet, and such providing the TID number together with each sensor. Once you have connected your channels to your hardware, the data acquisition system will automatically also read out the sensor ID number, and then you can easily import your data from your test point plan to your test database, and all the settings are imported automatically without manually typing in the numbers and parameters again. The fourth option is the TEDS configuration for transducers. You can store already information in a transducer electronic data sheet. This can already be done, for example, in a calibration laboratory. The scaling information, the validation date, for example, for the calibration can be stored in that TEDS information. Once you connect your transducer to your data acquisition system, the information is read out automatically, and the channel is set up according to the settings of the TEDS. In this slide, I'll show again the overview of the building blocks and the workflow for the configuration. So I've introduced the different workflows, starting from the manual setup of your system. Second option was to use the wiring-based mapping with a test point plan and a merge procedure. The third option was to use the ident-based mapping with a TID number. And the fourth option is most that is used in parallel to the other options is a TEDS-based setup for transducers, for example, load cells or displacement transducers. This can be used. If we arrange different workflows in terms of setup confidence and certainty, you will see that the confidence and the certainty increases when you look from the left to the right in terms of manual mapping, wiring-based mapping, ident-based mapping. When we look at the pros and the cons of the manual mapping, the pros are it is a simple workflow process. No specific format of the customer data is needed. The cons are there is a high probability of transcription errors. the mapping of the sensors and the amplifier channels is difficult, and you can easily make a mistake. Transcription of configuration data from customer files to DAQ database is very time-consuming, and frequently changing setups are difficult to handle in this case. If you use the wiring-based mapping, the pros are you have the possibility to set up your system before you get your hardware in hands. That is also lowering the possibility of transcription errors. You have a quick configuration of frequent changing setups is possible. Working with different DAQ system configuration is possible with a minimal effort. And you can increase the utilization of your DAQ system because of that. So the net operating hours will increase. The cons are the manual mapping of sensors and amplifier channels can still cause errors, and data to be input, you have to use a predefined vendor format. Then, looking at the ident-based mapping, the pros are a preliminary setup is possible, lowering the possibility of transcription errors, quick configuration of frequent changing setups. Working with different DAQ system configurations is possible with a minimal effort. An automated procedure minimizing the probability for mapping errors is used, and you have a maximum utilization of your DAQ system. The cons are additional hardware is necessary, in this case the so-called TID or ident board. Looking at a TEDS setup for transducers, the pros are you have the setup data is tightly assigned to your transducer, so mistakes are avoided. You have a quick configuration of frequent changing setups, automated setup, and for example check for calibration validity is possible. And you have a maximum utilization of your DAQ system because it is very easy to set up the data acquisition system. This is done usually automatically when you connect the transducer. The cons are, again, you would need additional hardware, the TEDS transducer and the data acquisition system supporting the transducer electronic data sheet, of course. Now I would like to show some examples how this looks like, so you get a better understanding how this different workflows are used. For the manual mapping, it is basically a table where you type in your parameters and manually put in the data for each sensor. And as already mentioned earlier, you have to be careful to not make any mistakes. You're always in the right column when you put in a gauge factor or a zero value. So that is a manual setup of the system. Looking at test point plans and merge procedure, in this case the input of all test-specific transducer and strain gauge parameters can be done before your test article is ready for running, so you can already start very early in your setup process for your test to define your settings of the sensors. Meaningful, definable default values help you to set up the test point plan quickly. It also includes channel grouping, allowing large channel systems to organize the channels in groups. And there's a definition of lookup tables for sensor types as well. Once you have your data acquisition system on site and you have created a database of your hardware, you can merge those two databases, the test point plan database and the data acquisition database together, and that will result in a status of your merge procedure, and you will get feedback whether all the channels could be connected, if calculations have been imported, for example, trigger channels have been imported, and so on. And the result of that merge procedure is a wiring diagram that now is your instruction to connect your sensors to your data acquisition system. So in this case, drain channel number 1 has to be connected to device number 1, slot number 9, channel number 1. Drain channel number 9 would have to be connected to device number 1, slot number 14, channel number 1. This way, once you have connected all your channels to your data acquisition system, you are ready to initialize and to run. The setup has already been done through the merge procedure. Import of configuration data from a database or Excel source according to the TID number can be done with the TID. It can be read out and put into the MS Excel directly with a USB to one-wire adapter. The TID code becomes part of the test database, and then the TID is part of the setup file. And the import can be done according to the TID code. Usually that data is stored in an Excel file, the sensor data together with the TID number. And that Excel file in this slide, you can see in the upper part of the split window below, in the screenshot, you can see in the upper part the Excel data, and in the lower part the data of the data acquisition system. Now you can define each column that has to be imported to the data acquisition database, and then the import can be done using drag and drop, and there's also an update function available if the source data has been changed. Important is that the identification column is selected. In this case, the sensor ID. You can see for different sensors different TID numbers, and in the upper part of the screen again you can see the sensor IDs that have been stored in the Excel sheet, and in the lower part you can see the hardware database where the TID number has been read out automatically by the data acquisition system. Now this data can be imported according to the TID mapping with one button click, and you are ready to initialize your hardware and run the data acquisition. There's also the option of the TEDS configuration, where you can store already data in a chip that then, once it is connected to the data acquisition, will be read out by the amplifier, and all the settings will be done according to the TEDS configuration in the transducer. The TEDS chip can be stored in the transducer itself. It can be used in the connector as it is shown in this picture, or it can be included into the cable. And on the right side you can also see another example of a TID board with 3 TIDs for a strain gauge rosette sensor. A clear defined channel sensor structure helps to avoid mistakes and confusion as well. So for the verification of your configuration, it is important that the channels in large channel count systems are clearly arranged and the channel configuration is available throughout the data acquisition suite. As you can see here, there are different options where how you can organize your channels in groups, and then later on in all the available dialogues where you have to select channels in online computations, or when you want to connect channels to digital indicators, for example, on your graphical user interface, you can use the channel selector and always easily browse through your system. An automated wiring check increases the confidence in the setup significantly. The wiring check function allows you with a shunt comparison to compare the reading of the nominal shunt and the measured shunt, and it can indicate with a single button click each sensor that has a problem, maybe a wire is broken or anything else is not connected correctly. You can see it immediately in a table view, and that helps you to increase the confidence in the setup of your configuration very easily. Having a quick look at a typical DAQ-system software suite, here is an example, Catman Enterprise. We have been looking now in that webinar mainly at the left two building blocks, the configuration and the data validation. That includes mainly the possibility of supporting all the different workflows that I have introduced today, and that should support you to select the most valuable workflow for your application. I would like to sum up the previous discussed items by stating how to effectively increase the efficiency of large channel count setups. The important points therefore are: you need a flexible data exchange with customer setup files, import and export functionality with automatic channel assignment, use of TEDS and TIDs to increase safety in setup and configuration, avoid manual input of data as far as possible, use of automated channel and wiring check functions. Let me now introduce some information about the activities and experience of HBM in large channel count applications. As you can see here, HBM has experience in different applications. On the left upper side you can see a static wing test that has been done at Airbus. On the right side you can see an F-18 full-scale fatigue test. Lower left side that would indicate a satellite test, and on the right side a blade test for wind turbine blades. The products that HBM provides are used for speeding up testing, boosting up test efficiency, maximizing test reliability and accuracy, and verifying component and product life cycle. Different application areas where these systems are used have been indicated before. This is mainly in structural testing, but also function and performance testing, test rigs, and monitoring applications. The product range of HBM includes the whole measurement chain from the sensor to the data analysis. As you can see here, there are some examples of the products that are provided by HBM, like strain gauges, force transducers, optical strain gauges, pressure and displacement transducers, a variety of digital data acquisition systems supporting centralized and also decentralized setup of your data acquisition, a mature software suite for data acquisition tasks, supporting all the relevant functions that are necessary to run a data acquisition on large channel count tests, including also interfacing to control systems. And it also includes a sophisticated software package for design, analysis, and professional data management. I would now like to thank you for your attention, and if you have any questions, please contact us. And I would like to thank you again that you have joined the meeting today, and we'll now close this presentation at this point.
Thanks, Johannes. If anyone has questions they would like to ask him right now, you're welcome to type them in to either the Q&A box at the top of your screen or the chat box, either one. And we can take a few of those real time, and any we aren't able to get to, we will definitely follow up with afterwards. One person asked if we can get a copy of the presentation, and I will definitely send a PDF of Johannes' presentation to everyone right after the meeting is complete. Johannes, I have one question. When do you recommend the wiring-based mapping?
The wiring-based mapping, as I explained it earlier, is based on mainly being able to connect also single channels. So there are different data acquisition systems where you can where you have one plug per channel, but some data acquisition systems that provide, let's say you can connect 8 channels on one plug. In this case, it is not. You could still use it, but it is much easier if you have a single connection for each channel. Then you can easily hook up and map your channels according to your wiring diagram later on.
All right, thank you. And someone's asking what kind of sensor types are supported by the automated wiring check function?
Basically, there are all sensor types available in that definition list. The sensor types could be, or the database could be extended if additional sensor types are required.
All right. Another person is asking, when do you recommend the TID versus TEDS?
Well, the TEDS is usually used for all types of transducers, for example, that have a calibration scaling information, or even maybe a polynomial curve defined. There you can use the TEDS, and then the amplifier would set itself up automatically. The TID is, I would say, nearly to 100% used with quarter bridge strain gauges.
All right. Another question, how does a TID know if they are wired to the wrong position?
Well, the TID number is read out twice. Once when the sensor is installed, and then at that time that information is read out automatically to an Excel sheet, the TID number, and then the TID number is then read out because it's part of the measurement chain. It is read out once it is connected to the data acquisition amplifier. And then, according to the TID number, the import is done automatically by the software as an identification column. So that lowers the probability of a mistake typing in maybe in the wrong column. Of course, if the wrong data has been put in the first place and that is assigned to the wrong TID number, then that is difficult to handle, of course.
All right, we've got a few follow-up questions here on that topic. Can the TID or TEDS be used on older sensors like load cells?
Yes. I mean, TID can be used in any for any sensor, and of course it must be supported by the amplifier. by the digital amplifier system to be read out. The TEDS is mainly a standard that most of the data acquisition amplifiers are supporting nowadays, and I would say nearly all of our load cells and the displacement transducers and other transducers are now supplied with TEDS, because it makes it much easier, as I said before in the presentation, when a transducer is calibrated, that the calibration data is already written to the TEDS in the transducer, and the software can even check the validation of the calibration date, for example, if it's still valid once you connect it to the amplifier, and it can flag a dialog or whatever, and can say, well, the calibration, that transducer is out of date, and indicate that you have to do a recalibration of that transducer.
And this is just a confirmation question. TID has location information only, no calibration constants. Is that correct?
That's correct. TID is only a worldwide unique 8-byte identifier.
All right. I think if we didn't get to your question, we will in the next 24 hours. You'll get an email from us with that answer. But we're going to close it out right there. Thank you all very much for attending. We're glad to have you join us. And Johannes, thanks again.